Good morning, everyone. We are Group 4 from the Department of Earth Resources Engineering, University of Moratuva. Today, we are excited to present our design project, Geothermal Energy Zone Classification using thermal imagery. Our team consists of myself, Dulakshi, and my colleagues Fasaid, Amit, Roy, and Lakshan. This project was completed under the supervision of Professor D. M. D. O. K. Disanayake and Engineer Sahan Sanjeevan. So, why focus on geothermal energy right now? Geothermal is a clean, reliable, and base load renewable source essential for the sustainable energy goals. Unlike solar or wind, it provides consistent power. But the big challenge is exploration. Traditional methods are costly, slow, and risky. You can spend millions on drilling before knowing if a site is viable. That's where our opportunity lies. With free, high quality satellite data from Landsat and Sentinel and advances in AI, we can now screen large regions at very low cost. Our project uses this technology to reduce risk in the early stage of geothermal exploration. This brings us to the main problem we are tackling: the high upfront cost of drilling, the slow and limited coverage of ground based methods, and the subjective process of identifying potential hotspots. To address this, our goal was to create an open source, web based platform that automatically identifies and classifies geothermal potential zones using multi sensor satellite imagery and artificial intelligence. In short, we aim to build a smart, fast, and user friendly tool to pinpoint the best location for geothermal energy exploration. Now, my colleague Fasail will walk you through the technical methodology of how we achieve this.
Thank you, Vaishnavi. To build the system, we design a modular and automated workflow. It starts with data ingestion and move to pre-processing and then code to analysis and layer fusion and finally to visualization and reporting. The key to making this work is ensuring all data layers are perfectly aligned. We achieve this by using a common 30-meter UTM grid. The entire backend is built using Python and leverage cloud optimized geotiffs for maximum efficiency. Our analysis is built on three core pillars. Let's look at each one. First, thermal analysis. We use thermal band from Landsat 8 and 9 satellites to calculate the land surface temperature or LST to find hotspots. We don't just look for high temperatures, we use statistical method called the SUD score to automatically identify significant temperature anomalies. This is much more objective and reliable. The core equation for converting the satellite data to Celsius is shown here. The second one is spectral analysis. Raw thermal data can be misleading. A hot city roof or dark rock in the sun can look like a geothermal anomaly. To fix this, we use Sentinel-2 satellite data to calculate spectral indices that help us mask these false positives. For example, we use NDVI to identify and mask cool vegetation and NDWI to mask water bodies and NDBI to downgrade the heat from urban areas. Third, spectral analysis. Geothermal fluids often travel to the surface through geological faults and fracture. These are critical pathways. Our system uses computer vision algorithm, especially edge detection and how to transform to automatically extract these linear features from the imaginary. This gives us a map of potential fluid pathways. Now, Minsat will show you how we implemented this method into a user-friendly web application and give you a live demo.
We have seen the why and how. Now let's see the what's our final working application. We didn't just build an algorithm, we built a simple interactive tool. It designed around four key features. First, simple interface. Just drag and drop your satellite files to start. Second, interactive visualization. Instantly toggle all your map layers, see the heats, falls, and the final prospective maps. Dynamic control. This is not a black box. You use live sliders to adjust the analysis and see the result change in real time. Finally, one-click reporting. When you are done, just click export for a file full PDF report with all your maps and statistics. Our technology is simple and fast. A Python Flask backend does all heavy data processing, while a Leaf.js frontend gives you a fast and interactive maps. Now let's take the quick tour of the map. Here is our main dashboards. Files are uploaded in the left. You see the key statistics like temperatures on the right. Now visualization. Here is our thermal heat maps. With one click, we can instantly overlay the geological faults on our system phones. Next, we switch the anomalies. This is the most important part. The app automatically flags the hotspots in the reds. The tools is interactive. You can click anywhere on the maps and see the points analysis box shows the exact temperature and data for the single pixels. As we scroll down, you see the combined analysis map. This is the best part. We fuse the heat data and the fault data, find most promising targets. Finally, the one-click reports. The systematically instantly generate the clean and professional PDF with all your maps and statistics. Now let's take the quick tour of the.
Thank you, friends. Next, I consider the results, effective false and positive detection. So, does this complex process actually work? Well, the results show that it does, and one of the clear success is in reducing false positive. As Fasaid mentioned clearly, future like cities or sun export rocks can often trigger false alarms. By apply our spectral mask using NDVI, NDWI and NDBI, we were able to filter out these non-geothermal heat sources. Our test showed 30 to 40% reducing closely flagged anomaly area, a huge improvement. This means the system can now focus on hotspots that are the much more likely to the truly geothermal in nature, saving the time and money in flow of the investigation. Next, I consider the integrated prospectivity maps. The ultimate goal is not just to find hotspot, but to create actionable intelligence. Our system does this by fusing the three key layers: the thermal illuminates, the structural faults, and the land cover mask into single prospectivity maps. We use technical called multi-criteria evaluation. We can assign different weight for each layer. For example, we can give 35% importance to false influence, 35% to the thermal anomaly, and 30% to the mask. This allows exploration term to the immediately focus this effect on the most suitable location. To summarize, our project and discuss next step. Here the lesson.
Thank you, Roy. In conclusion, our project has achieved four key things. First, we successfully built an end-to-end automatic system that transforms raw satellite data into actionable geothermal prospectivity maps. Second, we demonstrated that the fusion of thermal, spectral, and structural data are high effective, significantly improving accuracy and reducing false positive compared to using thermal data alone. Third, our open source web-based approach makes early stage screening low cost, scalable, and reproducible for any team anywhere in the world. And finally, our system bridges the gap between complete academic research and the practical need for a decision support tool that can be used by non-specialists. Future work. This platform has a very strong foundation and there are several exciting directions for future work. We plan to incorporate more data layers like digital elevation models and regional geophysics to better model the subsurface. We also aim to extend the machine learning path using advanced models like random forest to use the data, which could uncover even more complex patterns. And finally, we plan to implement time series analysis to look at data over several years. This will help us distinguish persistent long-term geothermal anomalies from temporary seasonal effects. On behalf of the entire team, I would like to thank you for your attention. We would again like to thank you supervisor and the Department of Earth Resource Engineering for their support. We are now happy to answer any question you may have.